Hello everyone. Today we're going to talk about displacement time graphs, velocity time graphs, and acceleration time graphs. Before we dive deep into how to analyze and interpret these graphs, let us first recall the definitions of displacement, velocity, and acceleration. So displacement is how far an object has displaced from its initial position. So let us take this number line over here, and let's say that this point is x equal to 0, and this is 1, 2, and this is -1, and this is -2. So let's say an object starts at x equal to 0, then moves all the way back to 2, and then comes back to -1. So here, in this case, the object is -1 away from its initial position, that's 0. So that means its displacement would be -1. Notice that this is different from the distance, which is the total amount it's traveled, which is going to be 2 plus 3, that's 5. Moving on to velocity. Velocity is defined as the rate of change of displacement with respect to time. And finally, acceleration is defined as the rate of change of velocity with respect to time. Those who are in calculus will probably notice this better, as this can be written as the derivative of the displacement, and this can be represented as the derivative of the velocity. Let us look deeper into the acceleration equation. Notice that delta V means the change in velocity, which can be written as the final velocity, which we'll take as Vf, and the initial velocity, which we'll take as V0. And let's say t is the amount of time it takes. Multiplying by t on both the sides, we get, this can be written as at is equal to Vf minus V0, and adding V0 on both the sides, we get our first kinematics equation, Vf is equal to V0 plus at. Notice here that Vf is a function of the time t. And also notice that this can be written in the form of y is equal to mx plus c, which is the equation of a line. Here you can see that the m, which is the slope, is represented by the acceleration, and the c, which is the y-intercept, is represented by the initial velocity. Let us now try to plot values for the velocity. Since the velocity is a function of time, we can have the y-axis is the velocity and the x-axis will be the time. Now, if I input time is equal to 0, you will see that the velocity is going to be v0. So let us just plot that point over here. And let's say at time equal to t, if you substitute t over here, you get that the velocity is vf. And we know that the graph going through these points will be a line with a slope of a, which is the acceleration. Now, notice that if I increase the value of a, then the slope of the graph will increase, and if I decrease the value of a, the slope of the graph will decrease. When a is equal to 0, we can see that the graph would just be Vf is equal to V0, which can be written in the form of y is equal to some constant, which is going to be a horizontal line. Looking back at my equation for velocity, if we solve for the change in displacement, we get that delta x is going to be equal to the velocity times the time. Notice that in this graph, that is going to be equal to the area under this graph. From this, we can notice that the area under a velocity time graph will give the change in displacement. Let us try to apply the same principle for this graph. So notice that this graph is a trapezium with its side lengths as V0 and Vf and height as t. The area of a trapezium is given by half into h into the sum of these two lengths. Applying the formula, we get that delta x is equal to 1/2 into v0 plus vf into t. Now, from this equation, notice that vf is equal to v0 plus at. Substituting that here, we get delta x is equal to 1/2 into v0 plus at to t. Simplifying the terms inside the parentheses, we get 1/2 times 2v0 plus at into t. Rearranging the terms, we see that this can be written as delta x is equal to v0t plus 1/2 at squared. Now, since delta x is the change in displacement, it can be written as the final displacement minus the initial displacement. So let us say that can be written as x, which is the final displacement, minus x0 is equal to v0 plus 1/2 at squared. Adding x0 on both sides, we get our second equation of kinematics, that is x is equal to x0 plus v0t plus 1/2 at squared. Notice that the equation which I have over here is a quadratic equation in the form of y is equal to ax squared plus bx plus c. That means that the displacement time graph will be looking like something like this, where this is the initial displacement and this is the final one. Now notice that if we draw a tangent line at any point on the curve, we will get the instantaneous velocity of the particle when this is moving. And this can be further seen or supported by the fact that the velocity is the derivative of the displacement, and the derivative always represents the slope of the tangent line. Now, I would like everybody to notice that these equations, along with these graphs, will only look the way it looks on this board if the acceleration is constant. And this, on a acceleration time graph, would look like this, a horizontal line. If the acceleration is not constant, then you will have to use other methods, such as calculus, in order to derive these equations.